Welcome everyone to the webinar Parallel Programming in OpendTect. I'm Kristofer Tingdahl. I'm a long-term developer of OpendTect, and together with me today I have a team of panelists. That is Nana Hemstra and Youngcheng Liu, and they are all developers. And this webinar is moderated by Renee Bork. Today we'll have a webinar that is a little bit different from the other webinars we have had so far, in that it targets software developers and those who are interested in software development. To be able to understand this webinar, it is required that you know C++, because all the examples will be in that computer language. Having said that, let's go right into the webinar and see what we will talk about today. First of all, we'll talk about why should we develop software that runs in parallel. Secondly, we'll look into different solutions to doing that in OpendTect, our experience about it, and finally we'll end with some questions. So, why do we want to develop software that runs in parallel? Well, there's a number of good reasons for that. First, we have recent development in the software of computers, and that is, the hardware of the computers, and that is in that most computers nowadays have more than 2 CPUs or cores, and they do inherently run software in parallel. New machines that all our users buy, there are at least 4 cores. The lifetime of the code that we write today is approximately 10 years. So if we look back into the code of OpendTect, we see codes that are easily 10 or some parts are even 15 years old. So the code that we are writing today will most probably run on many processors, maybe even up to 64 or 100 or something like that. And if we don't adapt the software to this, all our software will be perceived to be running very slow, and that is not what we want to do. Now, there are a couple of problems here. One of them is that our programming methods are fundamentally sequential. That is, we say to our software that we should first do A, and then we should B, and then C. Now, if we run software that is written for sequential execution, it will only use a fraction of the computing capacity on the workstation that we're using, and thus our clients and our users will not be very happy about that. Another problem we're facing is that tools for parallelizations are platform dependent. Now let's go into OpendTect and what is done about parallelism in OpendTect. We'll have a couple of examples. We'll talk about independent loops and how they can be parallelized. We'll talk about threads, queues, data synchronization, and all these tools are available in the basic library of OpendTect, and I will go through them all thoroughly. So you will, if you don't know what any of these are, don't worry, we'll go into that eventually. So let's look at parallelization of independent loops. And first of all, an independent loop is like a for loop or something that is done many times, and it does not really matter in what order it is made. Here I have a for loop that starts at IDX equals 0 up to size, and then I do a computation. But it doesn't really matter if I do from size -1 to 0. It doesn't really matter here. And that is what we call an independent loop, because each calculation is independent from each other. Now, how do we parallelize them in OpendTect? First of all, we have to create a separate class for this calculation, and it has to inherit parallel task. And the parallel task will take care of almost all the administration around the parallelization of this independent loop. We have to have a couple of functions implemented on this class. First of all, we have to have a size. That is how many times we will run the loop. And if we have the size, then we probably should have a constructor where we can set the size. We have a number of iterations. That is basically how many times this loop should be run. And finally, we have to have a do work function. And that is the function that will actually run the loop. And the do work function has to be written in a way that can be run in parallel. That is, it cannot read or write, it cannot write into a common shared object, such as objects on the object at the same time. You can certainly go in and read here, but if you want to write into common variables, then you have to have synchronization. We'll talk about that in a short while. Now, in the do work function, we implement the for loop, but here we start with the we get two variables here. That is the start, we get the stop, and basically that tells us what part of the overall loop that we should run. So in this case, we should start at IDX, which is stop when we reach stop, and we run these, and we return true because we're successful. If we do this, our original code can be transformed into something like this. So we create an instance of my class, and then we call executed. The Boolean variable that goes into the execute function is whether or not it should be run in parallel. You can force this to be run in single-threaded mode by putting in false here. We'll talk a little bit when that can be appropriate later in the webinar. Now, we can extend this parallel task a little bit or fine-tune it in various ways. First of all, we can put in a function that is called do prepare. Do prepare function is run before the do work, and it's run in single-threaded, and it will tell you how many threads that it will be run in. And then we have do work, no real change there. But we also have a do finish that will be run once all threads have stopped working on this. And there you can wrap up things, you can collect data, and so forth, and make everything in order before you are finished. We also have two functions to fine-tune the performance of a parallel task. First of them is max number of threads, which is a maximum number of threads that this particular class can be run in. Also, we have a minimum thread size, and that is where we specify that each chunk of this of the do work cannot be smaller than a certain size. If you have a loop that goes very quickly, you may want to return a large value here, because it's not really efficient to do all the administration of multi-threading if it's, say, less than 10 iterations, or maybe 100, or maybe 1,000, depending on what you are doing. There is also a need to be able to show the user what we're actually doing and let the user know what we're doing. And in order to do that, we put in a condition inside the loop. We can ask for each loop, should we continue? Because the user may say, well, I want to pause, or I want to continue, or I want to abort the whole calculation. And you want to catch that somehow, and you do that in this in the should continue function. Also, you want to tell the user how you're doing, if you're performing well, or how much you have done. And you do that by telling for each iteration how much you've done. So you call the add to number done function. Also, you can say, give a message telling something intelligent to the user what you're doing. And you can also say what the unit of the number done is. So it can be number of traces processed or something like that. If you do that, and you also do the following, you create a UI task runner, which is a UI class. It's defined in UI tools. Then you can give your class that inherits parallel tasks, you can give it to the task runner executed. If you do that, you will get a nice progress bar automatically for your for your calculation. And the user will be able to stop it or pause it temporarily or abort it. Now let's look at dependent calculations a little bit and the tools we have for that in OpendTect. And there's a couple of instances we need dependent calculations, and that is when threads have to exchange information with each other, and or variables. They may normally not be read or written in parallel. They have to either be read or they have to be locked and written, and so we need synchronization for that. There are a couple of tools for that in OpendTect, and let's start to do how to start things in parallel. For that we have threads. And a thread is really a sequence of instructions that are run at the same time as other thread. OpendTect has one thread which is called the main thread, but we can essentially add any number of threads to the system, and they will all run in parallel up to the number of processors that we have on the machine. If we create more threads than we have processors, well, then we have to it will start scheduling them, and they will all not run at 100% all the time. So let's look on how the thread is defined in OpendTect. This class is found in include basic threads.h. It has two constructors. It can either take a void static function or it can take a callback, which is OpendTect's way of calling a certain function on a certain object. It has a stop function. It is called stop functions in OpendTect 4.2. Stop is, however, not a good description for what this function is doing. So in OpendTect 4.3 and above, it is called wait for finish, and that is exactly what it's done. When we don't want to run the thread any longer, someone has to destroy it and stop it, and basically you call the stop function, and then that thread will wait for this thread to finish. There's a convenience function. You can get an identifier for the current thread, so you can compare and know which thread M is running right now and which thread am I in. So if we want to have an example of how we can use threads in OpendTect, let's say we have a class A. It has two different functions in it. It has a load data function that takes a long time to be run, and there's also a display data function, and that display data can only be done once the data is loaded. We can have a function called init that does that. It inits the function and it displays the it loads the data and it displays the data. And the user will sit and wait for this to finish for a while, because loading the data takes time, and then we display the data. What we can do, of course, is we can let the init function just start the process of loading and displaying the data in a different thread. Let's look on how that is done. So we start with the class A. Now we start with making a callback function that will actually do the work for us. And this is, if you haven't seen this before, it's a typical structure of a callback in OpendTect. It returns a void. Normally it has a CB function or a CB in its name, and it takes a pointer to a callbacker. That is what we call a callback. And this is this one will just do what was in the init function. It will load the data and it will then display the data. We have to have a thread on the class that will actually do this for us. And if we have a variable, we better have an initiator for that variable. And then we have an init function. So when the init is called, we create a new thread. And then we have this funny little macro here. And that essentially says that when this thread runs, it should call the load and display CB function on this class, which is class A. And this is the pointer to this class. So We start a new thread, and when that thread starts, it will call the callback for us. Also, we need to have the structure to close this off, and that is essentially something like this. If we have a thread, then we stop it, and once it is stopped, we can delete it. So if we look at the application, so if we, sorry, I'm missing something here, but so what happens when someone calls init, it will return immediately, and the loading and the display of the data will be done in the background. Now, let's look at some problems we have with this code, and that is basically associated with cost. And the problem is that each thread is created from the operating system. So when I create a new thread, there's a number of calls that are done into the system. Another problem is that each thread has its own stack. So if we have many, many threads, it will eat a lot of memory in our system. So we can conclude it's not optimal to create and destroy threads frequently. And that is why we have created queues. And queues is a sequence of a queue is a sequence of jobs that are run on a number of shared threads. So each job, each loading does not have its own thread. It shares threads with many other jobs. So the system will set up a number of shared threads in the system. Normally, I think the default in OpendTect is that it's 2 times the number of processors on the system. Jobs are put in a queue, and it's run by one of the threads. And this is much more lightweight than having dedicated threads, because we have a fewer number of threads, which take up much less resources. So let's look on how that is implemented in OpendTect. First of all, it's available from OpendTect 4.2, so it's quite recent. The class is implemented in Threads Work Manager. Again, it's available under include basic thread work manager, I believe. You can create your own manager, or there is a static one available that you can call using the TWM function. In OpendTect, you can add and remove queues. And each queue can be either single-threaded, multi-threaded, or manual. And we'll discuss these different types in a short while in this webinar. So first of all, let's look at the Work Manager class. And this is not the complete definition of the class. It's a subset of function here. But we have functions to add a queue, and there you say the queue type is either manual, multi-threaded, or single-threaded. You can remove queue, which is you're given the queue ID, which is returned when add queue returns. You can add work. Now, this class accepts a multitude of different types of works. So there is a wrapper class called work in here, and that class will put in callbacks and so forth. You can get a callback when it's finished. You have to give it which queue it should go into, and if you want to be a little bit mean, you can actually have to go first in line in the queue. There is a static queue ID, and that is a multi-threaded general-purpose queue that is sitting in the system that is created on startup. And again, we have the static functions to access an instance of this class in OpendTect. So let's go back to the class A we just had. And we have an init function that calls the load data and then the display data. The problem was, of course, that the load data and the display data took a long time. And the display data can only be done when the data was loaded. Now, let's look at the rewrite of this class in using queues instead of threads. Again, we start with the load data and the display data function. Then we have a callback that will do that, just that, load data and display data. The init function is now a little bit different. We don't have any dedicated thread in the class. So the init function will call the static instantiation of the thread work manager. It will add work, and it will take the callback. So we have the wrapper class with the callback in it. We have a pointer to callback that should be called when it's finished, and we don't have one in this case. We want to use the default queue ID, and we're nice. We're not putting this first in line. So what will happen now is that when init is called, it will put the task to run the load and display CB function. It will put that task on the queue, and when in due time, it will be computed. If there are threads available, it will start immediately. If there's no threads available, it will wait for its turn. But the init function will return immediately. So if we'll look at the main thread, let's now take the example that we actually want to load 10 of this of the class A, 10 instantiations of the class. We would then have a loop from IDX equals 0 to IDX is less than 10. We create a new class each time in the loop, and we call init on that class. And then we can do various stuff, and eventually the load data and display data are running in the background in parallel. Now, we'll come back to this class in a short while, but let's talk a little bit about thread synchronization in OpendTect. And we have a number of classes that will do that for you. And generally, they regulate access to shared resources in different ways. They help communicate between threads. And the reason for this is when we have a shared resource, like, for instance, a traffic intersection, we have a need to regulate that only one vehicle is in there at any given time. And if multiple vehicles are in the same intersection at the same time, we have a problem. So that is basically what we mean by regulate access to a shared resource. Another one is to communicate between threads. If you have been out driving and if you're out driving on the freeway and suddenly you see the car in front of you, see that the brake lights goes on his car, you know that you better make sure that you also start braking or slowing down so you don't run into him. So that is very similar to a thread communication. You communicate and tell another thread what's happening, what's going to happen, or so forth. In OpendTect, we have 4 different classes for synchronization. We have a mutex, and a mutex grants an exclusive right to use a certain resource. We have the read-write lock, and the read-write lock will allow multiple threads to have read access to a variable. But if someone wants to have a write lock access or write access to it, it has to wait until all the readers are out, and then once it is granted the write lock, it knows that it is the exclusive writer to that object or to that shared resource. A condition variable is a variable that you can use to wait for something to happen. You may have a thread sitting and waiting for another thread to finish, and once it's finished, you want it to continue or something like that. And you can have, that's a condition variable. A barrier is a quite powerful tool. If you have multiple threads working on the same calculation, but the calculation have different phases, and you want to guarantee that no thread is starting on phase 2 before all threads have finished on phase 1. And then you put up a barrier, and basically it will stop. Each thread will wait until all the other threads come and wait for the same barrier. So you can divide the calculation in such a way. Now, if we don't have a synchronization, we'll go into a little bit or an example of what could happen. So say we have a compute function that computes something on an array. But while the calculation is ongoing, the array is not fully filled in. It may be not a number of values in there, so forth. But the problem is that while we're waiting for it, or while it's calculating, a display function is called for the same array. The problem is, of course, that the display function is quick, it will finish soon, and it will display the messy array. And the computation eventually finished, and the array is good, but on the display it's still sitting in the old array that is messy or not nice. And this is actually quite a good example in terms of that normally it does not just display wrong values or something. It normally just crashes on you, and you will get spurious crashes that are very, very hard to resolve somehow. So let's see how this example can be solved by using threads or thread synchronization. So what we do now is we have a mutex on this class, and we use the mutex to regulate the access to the array. So before starting the computation, thread 1 will lock the mutex that will start the computation. At the same time, thread 2, who wants to eventually display, he also tries to lock. But he will not get access to the lock immediately because the thread 1 has locked it. So eventually the computation finishes, the array is good, thread 1 unlocks the mutex. That means that thread 2, or another thread, gets access to it, and he can then display his array, which is now a nice array, and eventually he can unlock it so that eventually someone else can display it again or compute something else on it. So this is a good example on a mutex that is used to regulate the access to the array. If we look in OpendTect, we can have the same example as we had before, but we'll put it on a new constraint. We say that the load data, for some reason, it may only be run once at any given time. Let's say there is waiting for it's dealing with a socket, and there's only one of those sockets in the system, or it's maybe it uses some shared memory with a different processor, or there's something about it that makes it only able to run at any given time. Of course, I can use a static mutex function to regulate that access. So I have my init function. It will look more or less as it used to. I will add the work, call the callback, to give it this whole thing to the default queue, and run it. And I have to rewrite my load and display callback a little bit, because I need to first lock my mutex, I need to load my data, unlock my mutex, and eventually call display data. And this guarantees that load data is only called single-threaded. Now, if we look at the main thread and the call of this, we have, again, we say we initiate 10 of these classes. We call the init function on them all. So we create them, and then we call the init on them. And we go ahead and do various stuff. Now, we actually, if we have available threads, all of these threads will start work on the work that I just added in the init function. The problem is that if I assign 10 threads to this, 9 of those 10 threads will only sit and wait for the mutex to unlock. So although I wrote this in a multi-threaded way, or at least I thought I did, I will still get single-threaded performance out of this, because I have 10 threads that could do something else, but they're sitting and waiting for this mutex to unlock. So I will now go into how we can use how we can use queues to avoid synchronization. and get much better performance than using the synchronization. And we'll do that by using the single-threaded queue, where many threads may add jobs, but we're guaranteed that only one of these jobs will run at any given time. And then we'll also talk about the manual queue. In the manual queue, many threads may add jobs, but nothing will be done with these jobs until a special command called execute queue is called. So let's look at the single-threaded queue. Again, we have the class A. We have the load data, which may only be run at any given time. We have now, again, the normal load and display callback, which first loads data and then displays data. Now we'll have a queue ID, which is a static function, a static variable that we have, and say somewhere in the CC file, in the source file, we'll initiate that to say -1, so we know it's not initialized. We have a constructor, and then if this is the first time run, we go ahead and we add this queue, a single-threaded queue, to the thread work manager, and that will be our queue ID. Then we have an init function, which will add the work. And the only difference we have compared to previous time is we now have the queue ID here, which is the queue ID I got in the constructor. So we're not adding this to the default multi-threaded queue, we're adding this to the single-threaded queue that we just created. And we're now guaranteed that any jobs added to this queue is run only in single-threaded. Let's see how that looks on the application code. So again, we started up with the 10 new class instantiations of A, and we call them all. And in the init function, each job is added to the queue, but since it's a single-threaded queue, only one thread will be assigned at a given time, and the remaining threads, they can do other things that is assigned to other queues, and I'm still guaranteed that it's performed in this single-threaded mode. Now let's go and have a look at the other tool we have in the queues, and that's the manual threads. There, when we add something to the queue, it won't be executed at all, at least not initially. But when a job is added, it won't run immediately. And many threads, many jobs will be added, and then they can really come from any thread. It doesn't really matter. And all jobs are run in the execute queue, it's called. So why do we have this? Well, in OpendTect we have one problem, for instance, where Qt does not allow updates from anything but the main thread. So say I calculate data in the background that I want to get displayed on a panel in OpendTect. I cannot immediately go and call the Qt commands to update this, because I'm not in the main thread, and then I may cause crashes or instabilities in OpendTect if I do that. So I have to go to the main thread and have the main thread update the data for me. Let's look on this in my class A again. Now I add a new constraint, and that is that the display data, that function may only be run from the main thread. So what I will do then is I will divide the load data and the display data into two different callbacks. I will have the load callback that we'll call load data, and I will have a display callback which we'll call display data. So the load CB may be called in multiple threads. The display data must be called from the main thread. So from outside, or the caller will tell me what the display queue ID is. We'll show how that is created or initialized in a few seconds. So we store on our object, we store the display QID. And we have an init function. And here in the init function, we only add the work CB. And we add that to the default QID. So this is run in multiple threads as it was initially. Now, we have to do a few things to get this working. And that is, when we have loaded the data, we want to tell the main thread, or sorry, the main QID, the display QID, that now it's ready to display the data. So we go to the thread work manager and we call or the add work function and say that now you can do the display ID, the display callback, but we don't use the main thread or the main QID, we use the display QID. So what will happen now is, the first thing I'll do is I have to create the display QID, and this is a manual queue, so it won't be executed automatically. I will start up my 10 instantiations of class A with the display QID. So I tell them where which queue to add the display to. It calls the init function, and what will happen now is that the low data is going to be run in parallel for all these 10. But at a certain point, we want to go ahead and make an update to the display. And then we'll call the execute queue for the display QID. So all the jobs that have accumulated in this queue over time have just been standing there, not been executed at all, until I call this from the main thread, and now it will all be done so that everything, all the display updates is from the main thread. Now let's look on our experience in DGBR Sciences in parallelizing code. And first of all, it is hard, both for myself and to make other developers think in terms of concurrency, that we're so tuned to doing things in sequence, that A happens before B, and not that A and B may happen at the same time, and sometimes B is finished before A. It's really hard to get your mind around that, and both for myself and I also see that at my fellow developers. We want to make it a priority to find single-threaded code. Well, a lot of the code is single-threaded, and in many times it doesn't care, or it doesn't matter. But I want all my developers to have a processor load up at all the time, so they can see a graph, see what's happening on the CPU when they're running OpendTect. And if they see that at a certain point the user has to wait for a couple of seconds or for a minute doing something, and the CPU is just idling at one single processor, well, then that is something that we have to address. That is a very good way to finding these things. Finally, one of our conclusions is that we have to develop parallel algorithms at the highest possible level. And I'll talk a little bit about that. And that is actually regarding some code I wrote myself about a year ago now. And we have an FFT transform. It is it's adapted from the Seismic Unix one, and we rewrote that in a way that runs in parallel. It runs beautifully. We're so happy about it. So say we have here a function that is called compute frequency spectrum from a seismic trace. So we set up the FFT transform, we set the data to the trace, and then we call the execute. And because this FFT inherits a parallel task. So we execute it and it's run in parallel. And I was so proud of myself. I'd put in a lot of work into this class. But to my surprise, it didn't scale it very well. That was simply because I had put the parallelization on the wrong level. Because I was doing this over a big trace buffer, a number of seismic traces, and for each of them, I ran this compute frequency spectrum, and for each of them, it will run the FFT transform in parallel and administrate that and divide each FFT transform into chunks and run them. Of course, it's much more effective to run the whole trace buffer as a parallel task, and that is what we mean by designing parallelism on the right level. So it would probably look something like this, that we would have a compute frequency spectrum function. We'll get a seismic trace, but we also probably would have like a Boolean telling whether we should run in parallel or not, and that Boolean is then passed down to the FFT when running. And then we'll just make a new class called trace calculator, have a number of iterations, have a do work function that for each chunk that it's assigned, it will call the compute frequency spectrum and basically put the parallel to false, because I don't want the FFTs to run in parallel. I want I don't want it to run in parallel internally. I want to have multiple FFTs run at the same time, because then I'm dividing my time much more wisely. I have much less administration around my queuing and so forth. So this is typically what I would do, and when we do this, yeah, this is when it starts scaling well. So to conclude, we've been talking about why we develop parallel software in OpendTect, or why we have a need for it. We've talked about solutions for this in OpendTect. That has been the parallel task, which we use for the independent loops. We've been talking about the threads and queues. We've also been talking about the synchronization, the mutexes, and also ways to avoid it, because there is a price to pay for that. And we've been just mentioning shortly some of our experiences doing this. If you're interested in this, we have a large number of resources available for you. First of all, everything in OpendTect is documented, so you can go to the online class documentation. We have a developers list that you can send your emails to, and either some of us or some of the other developers externally will answer to your email. And finally, I want to mention we have the ability to do training in OpendTect. We can come to your company, or you could come to us, and we give you a day's training in developing in OpendTect. Now, this is not a live webinar, so we won't have any times for questions at this time. Should you have any questions, I would ask that you write those to developers at opendtect.org, and we'll certainly answer them. Thank you very much for your time, and have a nice programming day.